This is the second lecture of my advanced nuclear physics course. So last time I gave you some overview of modern, let's say, nuclear physics. And throughout my lecture, I will explain microscopic description of nuclear many-body problems. And this second lecture, I will explain the Hartree-Fock theory and density function theory. And those are also used in the field of condensed matter physics. Let me check the microphone. Okay. Yes. So, okay. So this time, I will focus on those very well successful theory in the field of nuclear physics. Okay. So this is just as to remind you the syllabus. So in this lecture located here, I will introduce what is Hartree-Fock and DFT. And after this lecture, I will introduce the pairing correlations on top of the Hartree-Fock theory and develop some theory to describe the collective excitations, but it is also based on the Hartree-Fock theory. So this theory is very important in my lecture. So the purpose of today's lecture is following. So I will explain what is the Hartree-Fock theory or Hartree-Fock approximation in the framework of the many-body physics. And I will present or explain the concept of the density function theory. So I will explain the difference or similarities between Hartree-Fock theory and the density function theory. This is one purpose. So to clarify what are the difference and relevance between Hartree-Fock and DFT. So in the end of the lecture, you will understand how a one-body mean field potential naturally arises within the context of mean field approaches. So those one-body potentials are necessary to establish the cell structure or to explain the magic numbers that was phenomenologically done by Meyer and Jensen. But in case of Hartree-Fock and density function theory, this one-body potential naturally arises. Okay. So to begin with, let me explain the rationale behind the non-relativistic treatment. So within my lecture, I will use the non-relativistic treatment for the nuclear many-body problem. Some guys use relativistic framework, but in general, I think non-relativistic treatment is justified. So let me explain. So the bottom line message is the nucleons inside the nucleus are not really relativistic. That's it. So to show this fact, let me explain from the knowledge you already know. So as I explained in the first lecture, the nuclear density is saturated. So this is coming from the experimental evidence of the A to the 1/3 dependence of the nuclear radius. Okay, so from that fact, we know that nuclear density is somehow saturated. Okay. So since there are two kinds of fermions, neutrons and protons, let's assume that the density of each species, neutron and proton, are just a half of this saturation density. Okay, now using the Fermi gas model, you can readily derive what is a Fermi wave number. So as you know very well, this is just related to the 3 times pi to the power 2, n0 divided by 2. to the power 1/3. So this is well-known dependence of the Fermi wave number on the density. Because there are two kinds of fermions. No, the spin up and down, there's a factor of one half. So you can just put this number into this formula, and you can get this Fermi wave number in the nuclear medium. 1.33, femtometer inverse. Okay, and then you can quantify what is the Fermi momentum and what is the Fermi energy using this fact. Okay, only this fact. The Fermi momentum is nothing but the h bar kf, and you can use the famous, popular relationship between h bar c. You should remember this number, around 200 MeV femtometer. This is very useful to quantify the numbers, to evaluate the numbers. So h bar c is about 200 in the unit of MeV femtometer. And you can just use this relationship to get this number, about 262 MeV per C. And at the same time, you can get what is the Fermi energy. You can put just the nucleon mass. It is about 940 MeV, as you may know. And you can just put these numbers here. So from this evaluation, you can get the Fermi energy about 36 MeV. So the question is if this is really relativistic or not. Okay, so the velocity, Fermi velocity can be evaluated in this way. And by just putting these numbers, mc square, h bar c, and kf, already given here, you can get this number. So the nucleons at the Fermi level inside the nuclei moves with the 30% of speed of light. It is quite fast as compared to our daily life velocity, but if you evaluate the Lorentz factor given here, it is more or less 1.04 or something. So it's quite small, okay? So the relativistic effect is expected to be small for the nucleons inside the nuclei. So this is the reason why we can use non-relativistic treatment to describe the nuclei and nuclear matter. Yeah, here I just put some notes that meant to mention that there are some people using the relativistic mean field approaches, right? And they are claiming that, the spin orbit interaction is important to explain the shell structure of nuclei. And they claim that the origin of spin orbit interaction coming from the relativistic effect. It is true for atomic physics. I agree that if you use some non-relativistic expansion for the Dirac equation, you can see the spin orbit interaction comes from the relativistic effect. But in case of nuclear force, the origin is the nuclear force. The strong interaction between quarks and gluons. So the state dependence and also the spin orbit couplings can be originated from the strong interaction. So not necessarily the relativistic effect. So anyway, so there are relativistic treatment, but in my lecture, I will use the non-relativistic treatment justified by this number. Okay, so now, if you agree with that statement, so what we should do, or our ultimate goal, is to solve the many-body Schrödinger equation. Okay, this equation, that's it. So if we could solve this equation, we know everything. We have many-body wave functions, and we can calculate any observable using this object. Okay. However, it is practically impossible, at least at present technology. So let me explain why. So what we'd like to solve is this, again, many-body Schrödinger equation, but in practice, it is very, very difficult. Okay, so the problem is twofold. First one is computationally too demanding. So for instance, yeah, so this, you see, this many-body wave function depends on the coordinates and spin and isospin for all the particles, and it is, yeah, everything is in those arguments of this wave function. So if we change the spin of one particle, we can have various other degrees of freedom. And so you should multiply all the degrees of freedom to evaluate what is the complexity. So the number of degrees of freedom of psi will be this 3 times 2 spin and isospin 2 and 2 times the power of number of nucleons. So it will be tremendously large. So for instance, for A equal 10, so 10 nucleon system, you can readily get 1 billion. Okay. And for the 100 particles, it will be 10 to the power of 107. So it is ridiculously large. Okay. So too complex. And also, okay, you may say, since we will have quantum computer, we may handle this complexity on some certain clever way. But to solve this, to treat these equations, we have to store the wave function on the HDD, right? So the memory will be enormously large as well. So 16 is a complex double precision, the 16 byte, times this degrees of freedom. And you can easily get 10 to 25 terabytes for 10 nucleon system, and 10 to 636 terabytes or so for the 100 particle systems. Okay, so it is impossible, right? Okay, so in other words, psi, so please remember this statement. So psi contains enormous amount of information, maybe too much. That is a important point. So we don't have to take care of all of the information. It is too much. And there is some way to reduce these degrees of freedom. And the second problem is the nuclear force. So we don't really know actual form of the nuclear interaction. But it is quite, yeah, maybe it is too strong statement. So we know we are developing the knowledge of nuclear force, but not perfectly. So we need, yeah, for instance, lattice QCD calculations are in progress to derive the nuclear interactions from the first principles QCD, but yeah, it is not done yet. So we know some attraction and repulsion and so on, but it is not so done perfectly. And also we may parameterize the nuclear interaction in some form coming from the symmetry assumptions and fit to the NN scattering data. Actually, there is such an interaction we call realistic nuclear force or bare nuclear interactions. But the problem is it contains some repulsive core, right? That I introduced in the first lecture. And it prevents to use some naive many-body technique to use their interaction. So there's some technical difficulties in using the realistic nuclear force. But one can do some method. One can use some method. But anyway, so therefore, we have to introduce two approximation. So one is the approximation to the many-body wave function psi. Okay, so the many-body wave function contains too much information, and we have to introduce some approximation to handle this problem. And the other one is an effective or phenomenological nucleon-nucleon interaction. Okay, that can be used to the Hartree-Fock theory that I will explain later. And yeah, try to explain non-experimental data by fitting the parameters. Yeah, so this is I already mentioned, but one can use, yeah, there's such a group of people doing ab initio type calculations using bare nucleon-nucleon interactions. Yeah. So, but there is huge discussions, and I will not go into the details about this ab initio techniques. So in my lecture, I will explain how to approximate the wave function and how effective interactions are used. Okay. So now I will explain what is a Hartree-Fock theory, and those are guys Hartree and Fock taken from Wikipedia, I think. Okay. So now, what is Hartree-Fock theory? So let's begin with the variation principle. So the Schrödinger equation can be derived with some unrestricted variation. So assume that the energy, total energy is given here. I mean, this is standard form of the expectation value. So the psi here represents the many-body wave function. Now, if you do variation with respect to the Bragg state of psi, you can consider this psi on the numerator and this psi on the denominator, and you can readily derive this equation. And we can require this to be 0 as a variation. And, you know, as I mentioned, this is the expectation value of energy. And this variation principle leads to the many-body Schrödinger equation. Okay. So now, what is Hartree-Fock theory? So we introduce an approximation to the many-body wave function psi. And the approximation is to make psi as a single theta determinant. So this is the point. So this is the end. So if you understand this, it's perfect. So the psi is approximated by a single theta determinant. So I just recall what is the theta determinant. So in this slide, I will denote theta determinant as a phi to distinguish from the psi. So the theta determinant phi is composed of single particle wave functions of neutrons and protons. And this is just a determinant with some normalization factor. Okay. And those are just different expressions. So we may, this is a shorthand notation of this determinant, or we may write this determinant as a summation over all possible combinations, I mean permutations, with plus or minus sign depending on the number of permutations. Yeah, so this is just what I explained here. Okay, so those are just notation. So these are theta determinants that may be used in my lecture. Okay, so just to remind you, these phi, small phi represents the single particle wave functions or single particle orbitals for neutrons or protons. Okay. Oh, and this is also normal relation for the single particle wave functions. So each single particle orbitals are also normalized to each other. So this is just a condition. Okay. So now let us derive the Hartree-Fock equation. So I just assume that the Hamiltonian takes the normal form. I mean the kinetic one-body kinetic term and general two-body interaction. Okay. So what we do in the following is to take an energy expectation value using the theta determinant, and later we will make a variation. And then we can get the Hartree-Fock equation. So first, let us see how to calculate the kinetic term. So this guy. So the kinetic expectation value of this kinetic energy operator here by theta determinant. Okay. And the second line here, I just put the definition of theta determinant. So 1 over n factorial is just a factor, normalization factor coming from ground ket states. Okay. And this left-hand side, I just use the last formula with permutations. And on the right-hand side, I just use the shorthand notation of the theta determinant. And I just put this operator here. So this is just I just put the definition. Okay. So now we can consider the permutations of this or this summation. So this provides n factorial terms from this summation. But the point is, every time you can make a change of the integration variable. Okay. For instance, there is a term which has, for instance, R1 and R2 are flipped. Okay, R1 and R2 are flipped with minus sign here because of the flip. But you can change the integration variable R1 and R2. Okay. But it causes the change of the rows or columns. Okay. And as you know, if we change the rows or columns of the theta determinant, it provides a minus sign. So this minus sign sitting here and another minus sign coming from this change of rows or columns will cancel out. And all the n factorial terms contribute equally. Okay. So we can remove this factor here, and also we can take this summation here. So we remove this summation here. Okay. So this, I hope you understand this jump here. Now you can do calculation easily. So now this one-body operator T hat acts on only on the ice coordinate Ri here. So other single particle wave functions phi star and phi are not affected by this operator. So you can make these overlaps except Ri, right? So as I mentioned, all the single particle wave functions are also normalized to each other. So you can use this relationship that provides a Kronecker delta except coordinate Ri. Okay. So only the possibility. So here remains this, the summation over all permutations for this single particle levels, but only the possibility which provides the finite value is this. So Guzai1 is 1, Guzai2 is 2, blah, 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 and Guzai n is n. And Guzai I equals to I. Only this possibility remains because of the Kronecker deltas. And you get this result. Okay. So if you understand, it's perfectly okay. And if you do not understand, please follow after the lecture. It is written, everything is written. Okay, so this is the result for the kinetic term. So this looks at the expectation value of one body kinetic energy operator and summation over all the orbitals. This is the result of kinetic term. And in the same way, you can continue to evaluate the interaction term, this two-body part, and the main part is the same. Main idea is the same. So this is nothing but the I just insert the definition as I explained in the previous slide. And again, we can I skipped that detail. So yeah, I already skipped this discussion of n factorial terms. So I jumped to the after elimination of the summation and this factor. So just you can get this. And now, again, the Ri, coordinate Ri and Rj are affected by this operator, but others are not affected by this operator. So again, you can use Kronecker delta except Ri and Rj, right? Then there remains two possibilities in this case. First one is just all Guzai1 to Guzai n are in the ascending order, 1, 2, 3 to the n. So in other words, Guzai I equal I, Guzai j equal j. But there remains another possibility. So we can change the Guzai and Guzai j. So Guzai I equal j and Guzai j equal I. So the number I and j is flipped. Even if we flip this index of orbitals, still you can get this object here affected by this operator, interaction operator. So there remains two possibilities, and you can get this equation using Kronecker deltas for all the other combinations, and the result is the following. So first one is the difference between first and second terms are the index I, j, or j, I. So in the first term, I is used for the coordinate r, and j is used for r prime, but the other one is opposite. So this is the so-called direct term and exchange term in the Hartree-Fock framework. Okay, so this exchange term arises from the fermionic character of neutrons and protons. And yeah, this is the result of taking the expectation value by Slater determinant. Okay. So good. So now we have an expression for the total energy associated with this sandwich, Hamiltonian and the theta determinants in the blood ket state. And you could get this formula. So this is the total energy. And now we can take a variation for the single particle wave function phi star here. And it is actually quite easy. So phi star, for instance, this kinetic term locates only here in the Bra state. And you can use this kind of functional derivative, but you can just use the Kronecker delta for orbital index I and K, and this index for coordinates that provides a Dirac delta function. And because of this Kronecker delta and delta function, you can perform this integral over R prime, and you can get this equation. Okay, so this one-body kinetic energy operator is acting on a single particle wave function. Okay. And you can do the same way for the interaction term. Okay, so this is, okay, phi star there, only here. Phi star is only in this Bra state. Okay, and you can take the derivative for first and second phi star here and here. And again, you can use this relationship. The difference is the Kronecker delta, the indexes are somewhat different. IK or JK or R and R1 and R2 because of this difference, location of the difference, taking the variation. And then you can just perform an integral and summation over the orbitals and use the Kronecker relationships, those relationships. And you can just, this is just you can rewrite these equations and correct the terms. And you end up with this equation. So first one is the so-called direct term, direct Hartree potential. And the second one is the so-called exchange or Fock term. The difference is for the direct term, you can perform the integral over the coordinate R prime within this parenthesis. So you can view this potential as a local one-body potential. Local potential. Local means it depends only on the coordinate here. On the other side, in this exchange term, you cannot perform the integration over the coordinate. So it depends on the R and R prime. So it is a non-local potential in Hartree-Fock theory. So Fock potential or exchange potential is non-local. Okay. So there is a single particle wave function here, which contains R prime, and here is an integration over the R prime with this potential. So this is a non-local potential. So anyway, you could derive the equations after variation, taking the variation of Hartree-Fock energy. So this provides you the Hartree-Fock equation. So this is a summary. So if you perform the variation without any restriction on the many-body wave function, you could get the Schrödinger equation. But we cannot solve this directly in practice, so we introduced an approximation to the many-body wave function And in the Hartree-Fock theory, we assumed that the many-body wave function is given by the Slater determinant, given here, represented by phi. And after variation with this, here I put just a condition Lagrange with the Lagrange multiplier epsilon to make sure that the single particle functions are also normalized to each other. But anyway, you can perform this variation and you can get the Hartree-Fock equation. So this is the Hartree-Fock equation. Okay, so small h Hartree-Fock represents the so-called single particle Hamiltonian here, which is in general non-local. So it contains the kinetic term and the direct potential, Hartree potential, which is the local in space, and also the Fock potential, which is non-local. So, and those are the representations of Hartree and Fock potentials. And as you can see, this provides you some integral differential equation, coupled integral differential equations. So you have single particle wave functions phi for several tens to hundreds nucleons, right? To describe as nucleus. And this equation is only for each single particle wave function. So how to solve this equation is the following. So you can start with some initial condition, some certain initial wave function. Yeah, any wave function is okay. So you can put some random Gaussian wave packets, or you may start with some harmonic oscillator wave functions, or etc. Any initial conditions are okay. So starting with initial condition, you can solve this equation for each single particle wave functions. So having a wave function, you can calculate the densities and potentials. And those calculations update or change the mean field potential. So the single particle Hamiltonian is also changed. So you can solve once again this Hartree-Fock equation with updated mean field potential. So you can repeat this procedure until you get the convergent result. So this type of iteration is so-called the self-consistent iterations or calculation. So you can solve iteratively or self-consistently until you get the convergent result. Okay, so this is anyway the Hartree-Fock equation that you could get by variation principle. So in the field of nuclear theory, the Hartree-Fock theory has been used widely since 70s. So it's for a long time we have been used this Hartree-Fock equation. And I will explain some effective interaction to treat this Hartree-Fock equation to describe the nuclear properties. But quite recently, after 2000 or so, people regarded that the Hartree-Fock equation or Hartree-Fock theory with effective interaction has close relationship with the density function theory, which has been used in condensed matter physics and quantum chemistry, quantum biology, and so on. And so I will next introduce what is a density function theory, and later I will explain what is the similarity and difference between Hartree-Fock and density function theory. Okay, so anyway, this is a summary of Hartree-Fock equation. Okay, So from now on, I will explain what is a density function theory, DFT. Okay. So what is DFT? So density function theory, I would say, is a theory which gives us access to the exact solution to the many-body wave function. So it sounds like it contradicts to what I introduced in the beginning. So let me explain. So what we like to do is, as I mentioned, to solve the many-body Schrödinger equation, this guy. But in practice, it is impossible because of too many degrees of freedom. But in the density function theory, what we do is to solve the constant equation written here. It is quite similar to Hartree-Fock equation. But the difference is it is written as a local in space, right? So it is much simpler than Hartree-Fock equation. It was integral differential equation. Now this VKS, this one body potential, this is important. So I will say, but this potential is derived as a functional derivative of energy density function here, epsilon rho. So I will explain, but the point is, there is a theorem, mathematical theorem, that proves that the many-body wave function psi can be given as a functional of one-body density. So psi can be expressed something like this with argument rho. So there is a one-to-one correspondence between wave function psi and one-body density rho. It is surprising correspondence, but please, for now, please just trust this statement. So psi can be given as a functional of density. And if you agree this, then any observable, which is given as an expectation value of any operators, can be expressed as a function of one-body density. So for instance, the energy expectation value, which is the sandwich of many-body Hamiltonian, is also given as a function of one-body density. Then, okay, and we can show that it is equivalent. So by solving constant equation, which contains energy density functional here, which is connected in principle to the solution of many-body Schrödinger equation. And by solving constant equation is equivalent to the minimization of this energy density function. And the solution becomes equivalent to the solution of exact many-body Schrödinger equation. Okay, so I will explain what's going on here. But the point is, this EDF, energy density function, is a key to open this box to get the solution of the quantum many-body problem. But yeah, as I explain later, so there is a caution. So the existence of such a functional is proved, but the shape is unknown. So from the mathematical proof, we know that there is a key, there exists a key to open this box to get the solution of the quantum many-body problem, but we don't know the shape. Okay, so the situation is really like this. So there exists some key, but we don't know which is the correct one. So the development of the key or energy density functions are also important subject in nuclear theory, which I will not going to display in this lecture. But there are many types of EDF, energy density function, and which are quite well developed that explain a lot of properties of nuclear many body problems. And I just mentioned here that there is a method to solve the concern equation as an inverse problem. Yeah, this is just to mention. So there is such a guy to try to pick. I mean picking. So since we know the whole, we may try to get the information and inversely create the energy density function. So there are such a effort to develop the energy density function in the field of nuclear physics. Yeah, but I will not go into the details. But there is a huge discussions and efforts to develop the energy density function. So now I will explain. Oh, wait. Maybe I change the order. Yeah, let me go this way. Okay. So again, this is another caution. So the density function theory, if you believe or trust the basic theorem, it is very powerful too. But there is yeah, we should be careful. So he is a Jedi of DFT. Okay. So in principle, everyone walks with DFT says, in principle, DFT is an exact approach. If we find the universal or energy density function, this is the key. If we know the key, it is equivalent to solve the many-body Schrödinger equation. But there is a dark side of DFT. So in practice, it would never be exact because we don't know the shape. So be careful. But yeah, so the Jedi of DFT or practitioners knows this fact. So yeah, they are trying to find the universal correct EDF. But yeah, you should be careful. So please keep in mind that we don't know the shape. But in practice, we know very good functions. So we can use it for application. Okay. So this is just a funny statement. But anyway, so DFT has shown great success in various fields of science. So Walter Kohn received Nobel Prize in chemistry in 1998, and after that, number of publications which contains DFT grows exponentially or rapidly. Yeah, it stops around 2013, but I believe it is more and more increasing. Yeah, rapidly in recent years. And for instance, we can apply DFT to describe complex molecules like fluorine, or at the same time, we can describe solid states. For instance, this is a silicon crystal, and those guys apply time-dependent DFT to describe the response of electrons by strong laser field. So anyway, so one can describe many-body system of fermions with great accuracy using the DFT. So to have a taste, the basic papers by Hohever and Kohn and Sham are more than tens of thousands citations. So and it is increasing rapidly. So now I will explain what's behind the wonder of DFT. So I will show what is a Hohever-Kohn theorem and Kohn-Sham scheme. that makes DFT solvable and yeah, with great success. So now I will explain in only two slides, Hohenberg theorem. And the original proof is very simple, and you can easily derive within one page. So let me explain. The assumption is following. So assume that two many-body wave functions, psi and psi prime, let's say, provide the same one-body density, rho. Okay. So there are two different wave functions with same density. This is the assumption. So different wave functions are different ground state. I mean, different associated with different Hamiltonians. So kinetic term T and the interaction terms V are the same, but they differ by external potential V and V prime. So as a result, I mean, as a solution of Schrödinger equation, you have psi prime with E prime, the total energy E prime, and psi with total energy E. So this is the assumptions and preparation for the proof. So now you can readily get the conclusion. So for instance, so this is the total energy, it's the energy expectation value of this Hamiltonian H with psi. But from the variational principle, you know that the psi prime is different. So if you take the energy expectation value of H by psi prime, it must be larger. Because psi is the true ground state, and psi prime is something else. So that holds this inequality. Now you can slightly rewrite the right-hand side, and you can add and subtract V prime and V. So initially H contains a V, right? So you can replace V prime, but subtract V prime. So this is just the addition of V prime and subtraction of V prime. So now this first term is E prime from this equation. And second term is difference between the one body external potential, V and V prime. Okay. On the other side, you can do exactly the same argument for the E prime. So E prime is the energy expectation value here, and which is smaller, always smaller than the energy expectation value by psi, H prime by psi. Okay? And you can get this equation. And now you can subtract A. You can add A and B, two equations, and you can get this, puzzling result. So this means, assumption was wrong, right? So this is the so-called, reduced absurdum in English, or highly for in Japanese. So this proves that the assumption is wrong. So it means psi and psi prime. So if the wave functions are different, it do not provide the same one-body density. So this is the first Hohenberg theorem. So there is a one-to-one correspondence between psi and rho. This is very important statement. So as I mentioned, the many-body wave function psi contains enormous information. But if you trust this statement, it can be represented by one-body density rho. And one-body density depends only on the coordinate, right? So the degrees of freedom is substantially reduced if you use this one body density instead of many body wave function psi. Okay.
Right, so,
Yeah.
so in theory, you can work backwards to solving the wave function by manipulating rho law. Right? Is that where we're going with this?
You mean
Because you know, if there's a correspondence between psi and rho.
so in principle?
Yeah.
If we may go backward, yeah, in principle, yeah. Or please keep in mind, always in principle. Yeah. But recently, no. Yeah, so it is practically impossible to have a many body wave function because it is too much complicated. But the point is we can work with one body density. So the one body density can be the fundamental degree of freedom. That's the point. So from this first Hohenberg-Kohn theorem, we can derive the so-called second Hohenberg-Kohn theorem that I already mentioned. So in principle, by solving many body Schrödinger equation, H and psi are connected, right? And also using the Hohenberg-Kohn theorem, psi and one body densities are connected to each other. So now, the psi many body wave function can be written as a functional of density because of this one-to-one correspondence. And then, if it is so, then any expectation value like this should be given. We don't know the expression, but in principle, it should be written as a function of density, right? Because the right-hand side depends on the one body density. Now, the energy expectation value can be given as a function of one body density, and we call this object as an energy density function, EDF. And by taking the variation with respect to the one body density, it in principle provides the ground state energy and ground state density through the variation principle. Okay. So this is the so-called second Hohenberg-Kohn theorem, and it provides us some, way. I mean, this is the basic concept of density function theory. So by minimizing the density, and by minimizing the energy density function with respect to density, we can, in principle, get the information of ground state energy and one body density of the two many body Schrödinger equation. Okay. So now, this is the second page. So in practice, what we use is a Kohn-Sham scheme to actually make a calculation or application. So what is the Kohn-Sham scheme? So according to the Hohenberg-Kohn theorem, we have the energy density function, which is a function of one body density. Now, what we do here is to introduce single particle wave function or orbitals, small phi here, and express the kinetic term just like a Hartree-Fock. This is an independent or let's say just a let's say independent particle picture. So this is a kinetic energy associated with the one body wave functions and the rest. So we just rewrite this energy density function as a summation of one body kinetic term plus something else, which is written as E prime. So this is just the introduction of this first term. And now you can make a variation with respect to single particle wave function phi star here. So as you may realize, this is quite similar to what we did for Hartree-Fock. So if you do this, you can get this equation. This is nothing but constant equation. So now you understand what is this E prime here. So this E prime contains all the information of the many-body system. So this EDF it is given by as a functional of one-body density, which is in principle connected by this with this right-hand side. So so we don't know the shape or exact formula for energy density function E law and E prime law as well. But if you have some functional, you can perform this variation. Then you can get this constant potential, one-body potential here, and you can perform self-consistent calculation. Okay. So this phi, small phi, corresponds to the so-called constant orbitals, which is similar to single particle wave functions. And you can calculate the one-body density as usual. So just the summation of this absolute square of single particle orbitals. And then you can solve this equation repeatedly, iteratively. Once you solve this equation, you can get new set of constant orbitals, which provides new wave function, new one-body density, and which provides new constant potential, and you update this term and repeat. So this provides you some mean field picture of the description. So even though you treat single particle degrees of freedom, single particle wave functions or single particle constant constant orbitals or single particle wave functions, what you solve is coupled nonlinear differential equations. So you solve single particle wave functions inside the mean field potential and update, then you provide, you get the one-body density and mean field potential, and inside this mean field potential, the next form of single particle wave functions are determined. So all the nucleons or all the particles generates the mean field potential, and each particle occupy single particle state inside this potential. So this is very similar to Hartree-Fock case, and DFT also provides mean field picture into the description. Okay, so now I show how it works in practice in nuclear physics case. So it has shown great success also in nuclear structure theory. So DFT in nuclear physics is the following. So if you have some EDF, a single EDF, you can describe all atomic nuclei using only the single EDF, without any adjustable parameter. Okay. So for instance, so again, remember this is a nuclear chart which shows the neutron number and proton numbers on those axes, and each boxes corresponds to different atomic nuclei. So the neutron number n and proton number z determines the kind of or one single nucleus. Okay, so when neutron and proton numbers are different, we regard those nuclei as different nuclei. So having neutron and proton number, you can solve the Kohn-Sham equation iteratively for a given EDF, energy density function. And after self-consistent calculation, you can end up with some ground state. And you can get the ground state energy and ground state density. And in principle, in practice, you can calculate various observable shapes, radius, and separation energies, and so on. And if you change the new input, neutron number and proton number, and you can solve the same equation by just changing the neutron proton number, you can get the ground state of different nuclei almost throughout the nuclear chart. So it is very powerful framework. And also, you can imagine, as I introduced in the previous lecture, you can imagine that we can gather a lot of tremendous number of neutrons, then gravity makes a bound stellar object called neutron star, and we can use the same EDF without any tuning. We can use the same EDF, work with the same equation, Kohn-Sham equation, and we can get collectively the nuclear matter properties. Like incompressibility, symmetry energies, and many other behaviors can be obtained using the same energy density function. So DFT provides us a unified framework, unified microscopic framework to describe finite nuclei and nuclear matter microscopically based on a single energy density function. Okay. And this is just an example. So this website is provided by University of Tsukuba Center for Computational Sciences. So they make some systematic calculation based on the density function theory for atomic nuclei. And if you access this web page, you can click on the atomic nucleus, each of the nucleus, and you can see how the shape of this nucleus looks like this, and you can change the view, and you can see what is the deformation of all nuclei throughout the nuclear chart. And actually, not only the shapes, but also various quantities can be obtained. So now, I will, in the rest of, I have 30 minutes, so I could slow down a bit. So in the rest of my lecture, I will explain what are the difference and relevance between Hartree-Fock theory and the density function theory. So you already saw some similarity between Hartree-Fock and DFT, especially the equation, what we saw in practice. So of course, as you may understand, Hartree-Fock and DFT are different, right? Because Hartree-Fock theory is just an approximation where we approximate the many-body wave function by a single Slater determinant. And the DFT is in principle an exact approach based on some energy density function, and it can be exact. So those are different, right? But in practice, Hartree-Fock theory with an effective interaction that I mentioned can be or may be regarded as Kohn-Sham density function theory. So this is actually behind the success of Hartree-Fock theory in the field of nuclear physics. Because from the beginning, since we didn't know the nuclear force, strong interaction, from the beginning, we used some effective interaction with Hartree-Fock theory. And we have developed Hartree-Fock theory with effective interactions, and later we realized it is some similarity with density function theory. Okay. So now I will explain, first of all, the difference between electronic system and the nuclear system. So the density function theory has been used also for the condensed matter physics, namely the electronic system. Okay, so in the case of electronic system, the Hamiltonian is well known, well defined. So it contains the kinetic term and the interaction term. For the interaction term, it is nothing but a Coulomb interaction between electrons. Okay, so we know very well the interaction between constituent particles, electrons. And if we consider an atom or a solid state, we need to treat the Coulomb interaction from the nucleus or ions, right? And people in condensed matter physics do not treat nucleonic degrees of freedom, of course. They just treat as a point particle, and they can calculate the Coulomb interaction from those atomic nuclei, just treating as a positively charged point particles. So in electronic systems, the interactions is very well known, just a Coulomb interaction. So you can develop DFT nicely because you can calculate the for instance, this E prime that I mentioned, it contains the, how to say, the H is, so this E prime contains the expectation value of the Hamiltonian by many-body wave functions. Since in electronic system, since you know the interaction, you can have a kind of exact form for certain part of the interaction. So you can derive, for instance, direct term for the Coulomb interaction, and you can also derive exchange term or Fock term for the Coulomb interaction. So you can use such potentials or such a term from the Hartree-Fock theory. So you know some part of important terms in this EDF already in the Coulomb interaction. So it makes the problem simpler in the case of electronic system because of the clear definition of interaction. However, in nuclear systems, as I mentioned, the situation is quite different. So in nuclear system, the kinetic term and Coulomb interaction exists. So Coulomb interaction between protons, right? But in addition to this, there is nuclear interaction, strong interaction between neutrons and protons. So, and it is quite complicated. So, as you may learn from the Sekiguchi-san's lectures, it contains the three-body interaction, spin-orbit interaction, tensor interaction, and repulsive core, and various state dependence. So there is something complicated. So interaction is not well known in case of nuclear physics. It is very, how to say, problematic. So from the beginning, especially in the 70s, it was unclear how to model the interaction. So in the people, people start thinking about the effective interaction. So with Hartree-Fock theory. So in practice, what people do is to introduce zero-range effective interaction or contact type effective interaction. So zero-range means, okay, so this is the two-body interaction as I mentioned in the derivation of Hartree-Fock theory, and people parameterize the effective interaction in this way. It looks somehow complicated, but yeah. But the point is, it contains the Dirac delta function here. So all the term is proportional to delta R1, Ri and R minus Rj. So it means this interaction acts only for the case where two nucleons at the same place, at the same coordinates, Ri and Rj are equals to each other. Okay. So, and okay, just to mention this T0, X0, T3, X3, and so on. Those are parameters fitted to reproduce experimental data. And also, W0 is the interaction. This term represents a spin orbit interaction. And as you can see, there are K, operator K. This is nothing but the relative, kind of relative momentum operator related to the relative momentum between two nucleons. And it contains the derivatives, nabla. So because of this, since the interactions are contact or zero range, it effectively contains some finite range effect through this derivative, nabla operator. But anyway, so people started already with complex parameterization of two-body interaction. An important point is here. So it also contains the rho alpha here. And this rho is a one-body density. So this effective interaction depends on the density itself. So, and the reason why people introduce this term is the many-body interaction, many-body force, especially the three-body force. So since this interaction depends on the density, so it contains some effect of matter around the nucleus, around the nucleus. And this term effectively describes the many-body force, especially three-body force. So anyway, so using this, the so-called SCARM interaction. This is the name of guy that proposed this interaction. We can derive. Actually, you can already know. You know already how to derive the equation. So you can use this form. Just plug into the formulas that I gave in this lecture. You can derive the total energy expectation value of the Hamiltonian by a Slater determinant. And if you do this, you can realize, you can get total energy is given by a functional of various densities. Not only one-body density, but also some kinetic energy density or the gradient of density or Laplacian of density and spin orbit density and so on. But anyway, those are kind of densities, various kind of densities And with those densities, this total energy is somehow represented. Okay. And thanks to these Dirac delta functions, everything becomes local, everything becomes some functional of local densities. You can perform the integration, and then you can eliminate all the redundant coordinates and end up with those local densities. Okay. So now you already, almost you are end of this conclusion, this lecture. Okay, so regarding the total energy with the scarm effective interaction as an EDF, the Hartree-Fock equation, scarm Hartree-Fock equation, can be regarded as a Kohn-Sham equation in density function theory. That's the point. So, as I mentioned, if we perform variation without any restriction on the many-body wave function psi, you can derive the Schrödinger equation, many-body Schrödinger equation. Okay. And this circle represents kind of variation space. It is unrestricted in this case. And now, in case of Hartree-Fock theory, you introduce kind of approximation to the Slater determinant. I mean, to the many variable function to be a Slater determinant. And this makes the variational space much smaller than the unrestricted variation. So with this restricted space, we seek for some better, best solution within this variational space. So with Hartree-Fock approximation, you could derive this equation, the Hartree-Fock equation, which is in general non-local. So it contains direct term and the exchange term, which is non-local. So those are the formulas that I gave you in this lecture. So now you can put the effective nucleon-nucleon interaction into here and here. So this V can be replaced with a complex scarf effective interaction. Okay, so as I mentioned, so Hartree-Fock and DFT is not equal because we restrict the solution into this smaller variation space. And in principle, DFT can get the exact solution. So it is completely different. So, but in practice, what we use is some effective interaction. And those, especially it contains the density dependence. And you can use this effective interaction and you can end up with this Scarm-Hartree-Fock equation. So the point is, this Fock term, which is non-local in space, this gamma f, becomes local in space because it contains the Dirac delta function. The integration over R prime can be removed from all the term in the exchange term here. And this exchange contribution also can be expressed by this local potential. So given here. So it is Hartree-Fock equation, which is local in space because of the zero range effective interaction. But this potential is given by just a chain rule. So the functional derivative of EDF or total energy E. So if you regard this total energy with scan effective interaction in Hartree-Fock theory as an energy density functional in the Kohn-Sham DFT, you may regard this equation as a Kohn-Sham equation. So that's the point. So although many people in nuclear physics community say we use Hartree-Fock theory or Hartree-Fock approximation, but it is actually should be regarded as Kohn-Sham equation in the context of DFT. And especially since the interaction contains the density dependence here, the Hamiltonian is not actually not rigorously defined. So this is also the reason why we should regard this as a DFT, not a Hartree-Fock, because the Hamiltonian is not well defined. So anyway, so this is the behind the wonder of success of Hartree-Fock equation, Hartree-Fock theory in the case of nuclear physics, and it should be regarded as density function theory. Yeah. So since we work with Slater determinant, we have restricted the variation space, but if we regard the EDF, this energy expectation value as an EDF, and if we correctly fit the parameters in the EDF to the existing data, it could be more and more correct one. I mean, it provides better and better results, and in principle, it can provide us exact solution of the many-body Schrödinger equation if we find correct universal energy density function. Okay, so this is the bottom line message. So scan Hartree-Fock and scan TDHF. So TDHF is time-dependent extension, and I will explain this time-dependent extension in the 5th lecture, I think. But there is a time-dependent extension also, which provides us TD-DFT, time-dependent DFT. Okay, so yet we have some more minutes, but I came up with summary here. So let me summarize this lecture number 2. So the takeaway messages are following. So this is one important point. So in the Hartree-Fock theory, what we do is to approximate many-body wave function by a single Slater determinant. This is true and widely used in various fields of science. So this is a Hartree-Fock theory. Okay, but in nuclear physics, what we use is some effective interaction, some density-dependent local nucleon-nucleon interaction has been used. Okay. As a result, the Hartree-Fock equations, which is in general non-local, becomes local in space. And yeah, you can regard this localized Hartree-Fock equation with effective interaction as a Kohn-Sham equation in the context of DFT. And yeah, I think this is a success. This is behind the success of the mean field approaches for nuclear systems. So in nuclear physics community, people describe a lot of phenomena within mean field, the so-called mean field approach, or Hartree-Fock, or relativistic Hartree-Fock, etc. Mean field approaches. But in many cases, behind the formalism of mean field theory, there exists the correspondence between the density function theory, because they fit effective parameters to the existing experimental data. So behind the success of mean field approaches in nuclear physics, there is a connection between the density functional theory, which I introduced today, and with DFT or mean field microscopic approaches, we can describe the ground state properties of all over the nuclear chart, and with the same parameter set, we can also describe nuclear matter properties inside the neutron star, thanks to the magical correspondence between DFT and many-body Schrödinger equation. Okay. So this is a summary, and in forthcoming lectures, I will in this lecture I focused on the ground state properties. So it is just a variational principle, but we neglected, for instance, the pairing correlations. So pairing correlations are kind of Cooper pair formation, spin up and spin down neutrons and protons form a Cooper pair, and it becomes a superfluid or superconducting phase. Actually, in a lot of situations, in many of nuclei and neutron star matter, neutrons and protons are superfluid phase. So I will explain in the next lecture how to deal with this superfluidity and superconductivity. And in the coming lecture, I will also discuss how to describe the excited states and nuclear reactions. Okay, so still we have 8 minutes or more, but maybe I can stop this lecture here. So if you have any questions, please ask. And also, please remember that I gave you an assignment in the first lecture, and please submit it until the deadline. Okay.
Potential design in order to provide the relation between the Hartree-Fock and field. It is
Accidental. Yeah. So first, they just for simplicity, they assume some localized effective interaction.
In terms of these operate in order to reproduce and then something.
Not NN scattering, but many ground state properties of nuclei, like the separation energies and binding energies, and nuclear matter properties like EOS. So many known data are reproduced by fitting the parameters. Any other questions? If not, okay, so you can.